Welcome back to our pre-recorded lectures for Thermodynamics, Phys 310. So today we're going to talk some more about temperature. So we started talking about temperature last time. We're going to continue talking about temperature this time. This is going to be lecture, come on. This is going to be lecture 3.1. And we're gonna continue our discussion of temperature, and moreover, we're going to talk about temperature scales. Temperature scales. All right. So, last time so far we've discussed basic concepts in thermodynamics in lecture 2.1, pressure in 2.2, and temperature in lecture 2.3. So, so remember last time we said that temperature was defined in terms of our thermodynamic equilibrium. Remember we said a thermometer is basically something that has some property which changes with temperature. We're going to read that property as an indicator of its individual temperature. And if it's in thermal equilibrium or thermodynamic equilibrium, let's just say thermal equilibrium. If it's in thermal equilibrium with another system, then we can read that other system's temperature, right? So now the question is, how do we compare thermometers, right? How do we set a scale that allows us to read various thermometers? So basically, I'm saying I can have low temperatures and room temperatures and high temperatures, and how do we have a uniform comparison between them? Can we use thermometer? So how do we set a temperature scale, right? Okay, so basically, we start with something arbitrary. Okay, so what I mean is, let's imagine that we're going to have the Celsius scale. So the Celsius scale is arbitrary, but nice. We're going to have 2 points, so we're going to have 100 increments between two fixed points. So we really are only going to have 2 fixed points, and everything else is going to be either interpolation or extrapolation, right? So for the Celsius scale, this was 0 degrees C, which was water freezing, right? And 100 degrees C, where water boiled. Okay. Now, this was obviously pretty arbitrary. You just took some ink, and everything in between or outside of those ranges is just an interpolation or an extrapolation from those points. Equivalently, Fahrenheit is equivalently arbitrary. So there, 0 was defined as the lowest accessible temperature. So that was basically a mixture of ice and water, which allowed, salt and salt with ice that allowed it to freeze, or salt and water that allowed it to freeze at a lower temperature than pure water, right? As we all know, salt your driveway, it it doesn't make ice melt. It lowers the freezing point so that at the outside temperature of the room or the outside, that's no longer a freezing point for the saline solution, right? And then the highest temperature was where water boiled, which was equivalently arbitrary 212 degrees Fahrenheit, right? Okay, so now we have two different temperature scales where we have interpolation and extrapolation, and we have to have some way to compare, right? So this, in fact, we can compare because we know that the water boils at the same temperature, right? So of course there's a conversion from degrees Fahrenheit to degrees C, which is 9/5 plus 32. So if I have 9/5 of my temperature in Celsius plus 32. Okay, so if I take my temperature in Celsius, take 9/5, add 32, I can get my temperature in Fahrenheit. Okay, so now here we see we have two different temperature scales. They're determined by fixed points, right? And we can have a method of converting between these temperature scales. All right, so the question is, okay, so now this is basically the idea behind temperature scales. We have fixed points and we have interpolations and extrapolations. And this is basically how we're going to deal with temperature. Now, the question, though, is do all thermometers work at all temperatures, right? So if I have, let's see, pick your favorite thermometer. Let's take the mercury bulb thermometer, right? So let's have that old school glass thermometer with mercury that came up to a certain level, right? Does this thermometer work, or it could be ethyl alcohol, right? Does this work at all temperatures? No, it does not, right? At some point, this is going to hit this top and it's going to be saturated, or the mercury would be so cold that it would be down here in the bulb, right? And so this would no longer work. So there's only some linear range in which this works. And so that's an important thing, that we actually, even when we have a certain thermometer, certain temperature scale, we're going to have ways of comparing between them, okay? I showed you some pictures at the end of last lecture. I tacked on some pictures of some thermometers in my lab. So there's like resistance thermometers. So we can measure the resistance of a material, like a metal. At some point, that metal, let's say, is going to melt if I go to too high of temperature. So it's not going to work. Or you could have some diffusion between it and its surrounding materials that make it no longer work. Certain materials, this one at some point will stop working because the mercury would freeze, right, and turn into a solid and it would no longer work. There's all kinds of ways in which thermometers can't work. And so we need a temperature scale which allows us to work on all of them in between. So the question is, can we make an ideal thermometer? Can we make a thermometer that really works over almost every temperature range? Can we make sort of almost an ideal thermometer? And the answer is almost. We can almost make an ideal thermometer. And to do that, we need to have a new concept, which is going to be an equation of state. Okay, so we're going to talk lots about equation of state and more in the next part of this lecture. But for now, I'm going to just tell you that the equation of state for an ideal gas is PV equals nRT. Okay, so this uses our thermodynamic variables, pressure, volume, and temperature, right, to define the state. Okay. So imagine that we fixed one of these thermodynamic variables, right? So I only need, for example, two of these to be variables, and one can be fixed. So fix volume, right? And you can make what's called the constant volume gas thermometer. Very likely, most of you have done this experiment in your lab, in one of your lab courses, where you had that little glass bulb and you surrounded it in this copper kind of mug, and you put ice water or you put a Bunsen burner, and you could explore how the pressure then varies with temperature, right? So let's do that. Let's imagine we're going to measure the pressure, okay? And we're going to have the gas inside is what we're going to be measuring the pressure of, but we're going to set that to be 0 degrees C. And that was where water, ice coexisted. And then you could turn it around and you could put your Bunsen burner under it, and you could make it so that the water is boiling, and you get 100 degrees. So you could measure the pressure here, and you could measure the pressure here, and you get a straight line, because you can see this is a linear relationship, the linear equation of state. And the cool thing about that is we can interpolate between it, but we can also extrapolate all the way to 0, right? So that very important point where the pressure goes to 0 now defines a new thing, right? So that's a new, so when pressure goes to 0, that gives us the temperature goes to 0, right? So when P equals 0, the temperature is defined to be 0. So this is very cool, and this is called absolute 0. Okay. Particularly love the concept of absolute 0 because there are really only 2 absolutes in nature that I know of. Okay. In all of physics, I can only think of 2 absolutes. So one of them is absolute 0, and the other is the speed of light. Okay, so the speed of light is another absolute, and you can't change those, right? And you can't go past them. I can't go past absolute 0, and I can't go above the speed of light, and that's it. Such a simple experiment, such a simple ideal gas law, and we can get an absolute of physics. So this actually allows us to now define a new temperature scale. And this temperature scale is actually my favorite one. This is the Kelvin scale. And as a low temperature physicist, this is the scale that I think about. I mean, when I read off today's weather, I obviously think in Celsius, but in my lab, I'm always thinking in Kelvin. So one is absolute. So the comparison between the Kelvin scale and the Celsius scale is very nice because changes in temperature are identical. That is delta T. So 1 degree Kelvin is the same as 1 degree Celsius. So it takes our sort of our arbitrary temperature scale, which was Celsius, and now makes it still have those nice number of interpolations, but now is going to make it absolute because 0 is one of our fixed points, right? So the conversion between Kelvin, and you're not supposed to write the degree, is 273.15 plus the temperature in C. Okay, so if you take the temperature in C and you add 273.15, you're going to get your temperature in Kelvin. Okay, finally, the one cool thing about the Kelvin scale is since it actually already now has one fixed point, which is T equals 0, right? So that's one of our fixed points in Kelvin, put our units. We only need one other fixed point to define the temperature scale. So this is actually defined as the triple point of water. You know what the triple point of water is? So the triple point means it's the point where you have a coexistence of water, ice, and water vapor. So you get a liquid, a solid, and a gas all at the same point. And that happens at 0.01 C, right, plus plus a hundredth of a degree above 0 C at about 600 pascals. Okay, it's just the definition where this happens, right? So now if I want to convert, so the temperature in Kelvin can now be defined as 273.16 times the pressure that I measure over the pressure at this triple point. Okay, so the pressure at the triple point, now I can take the pressure, any pressure I measure, divide it by the pressure at the triple point, and multiply it by 273.16, and I can get the temperature in Kelvin. Okay, so let's pause there, and we're going to go on, and I'm going to continue to, oh, actually, let me do one more thing real quick. So last time we talked about a sense of scale, right? So we talked about how, like, kind of the range of pressures that one might experience. Okay, so for a feeling, for a sense of scale. First off, you know, when you think in Kelvin, room temperature is about 300 Kelvin. Okay, 300 and a bit, but regardless. If I were to take the dominant component of air, which is nitrogen, so N2, and I were to cool it down until it liquefies, so I get liquid nitrogen, that happens at about 77 Kelvin. If I were to then continue on, and I were to cool another isotope that cools at a lower temperature, another gas, the very last gas that I can use is helium. Helium is the lightest element. It's the same mass as molecular hydrogen. Molecular hydrogen, because it has some van der Waals attraction, because it's a non-chemically symmetric molecule, it actually freezes at more like 14 Kelvin. Liquid helium freezes at 4.2 Kelvin, or sorry, liquefies at 4.2 Kelvin. So we get to all of these temperatures in my lab, and then we get much, much colder. So this is the starting, so 4.2 Kelvin is the starting point for a lot of experiments in my lab. But, you know, this is actually quite warm when you start to even think about the universe. So when they measure the cosmic microwave background, so this is the COBE experiment, C-O-B-E, I believe. So we measured the temperature of the universe to be 2.73 Kelvin. Now, that's not even the coldest place in the universe. There's something called what's it called? Oh, there's a nebula. Let me find the name and I'll bring it up in class. But there's a nebula that's about 1.5 Kelvin. It's like a crab nebula. I don't know. Star nebula. I can't remember the name. But that's really interesting because there's an interesting phase of liquid helium that happens at those temperatures. So the superfluid phase of liquid helium. So that actually makes me think that there's possibility that there's superfluid helium somewhere in the universe. Kind of fun. Okay, so the lowest temperatures that, so the dilution refrigerators in my lab. So a dilution refrigerator. So that is That is a very special kind of refrigerator that I have in my lab. And they both go to about, actually I got one of them to 7.5 millikelvin just a couple of weeks ago. It wasn't working right and I tweaked it up and then we got it running nicely to 7.5 millikelvin. That's not the coldest place in my lab. Actually, one of our fridges uses another kind of cooling, which is called adiabatic nuclear demagnetization. So let's just call it DMAG. And with that, we've gotten down to about 700 microkelvin. So that's on a volume big enough to cool a can of beer down. So could get we've never done that. That would be crazy. A bad use of taxpayer dollars. Or is it? Actually, the LeBlanc lab. So the LeBlanc lab gets their rubidium atoms. So this is actually a little gas of rubidium atoms. They can get it down to about 10 nanokelvin. Right? So that's 10 to the minus 9 Kelvin. And I think the lowest temperatures that have ever been recorded have to do with the spins of nuclei. And that's picokelvin. Or 10 to the minus 12 Kelvin. So that's about as cold as we've ever gotten. All right, so let's go to the opposite scale. I want to think about how hot some things are. So that's cold. That's where things get the most interesting, in my opinion. But on the other side, copper melts. And I think it is 1358 Kelvin, I believe. Let me just check. Yeah. But you actually have something in your house, well, maybe not anymore, that's even hotter. So the filament of a light bulb. So a tungsten light bulb can get to about 3,000 Kelvin. 3,000 Kelvin. I was writing 3K. 3KK. So that's actually why, like, if anybody's into like colors and lighting colors, they'll talk about the colors of the black body spectrum in terms of thousands of Kelvin. But the sun, the surface of the sun, that is, the surface of the sun is about 5,800 Kelvin. So actually, as an exercise, go calculate what the peak wavelength of the sun is using Beam's law. But the center of the sun, they estimate to be about 10 to the 7 Kelvin. So that's quite extreme, and I can't even think about what kind of temperatures are like that. Okay, so that's good for now. Next time we're going to continue on thinking about the international temperature scale.